with an HTTP call over the network. So when it comes to integrating your modules in a synchronous fashion, be aware that you will have to re-implement this communication in one way or another when you decide to extract some of the modules into a separate service. Another way that two modules can communicate with each other is using messaging. In this example, the communication between two modules is asynchronous, which means there is no temporal coupling. So if one module wants something to happen in the other module in the system, it's just going to publish a message. This could be a simple document using JSON, which is sent over a message broker, and then any of the modules that are interested in this event or message can subscribe to receive this message from the message broker. The beauty of this type of communication between modules is that you can have any number of consumers. So if I want another module to start reacting to a specific message, I'm just going to subscribe to this message from the message broker. Now, when it comes to implementation details, the message broker could be just an in-memory message bus. You could implement this with something like Mediator. Mass Transit also supports an in-memory message bus, which is also what we are going to use when we start implementing our application. Another benefit of using messaging to communicate between modules is that it works the same in a distributed environment. The message broker is now going to be a distributed message broker, which does mean you need to introduce a new infrastructure component. And let's say this is RabbitMQ, and you would continue publishing and consuming messages in the same fashion. So these are just a few high-level ideas and considerations when it comes to module communication, but as I said, we are going to take a deep dive into this topic in one of the next chapters. Another important constraint that we need to enforce between our modules is the data isolation between the modules. Overall, I have identified 4 levels of data isolation that you could apply to your system. At level 1, we have data isolation using separate tables. At level 2, we have separating by schemas or logical isolation. At level 3, we have separating by databases. And at level 4, we implement data isolation using separate databases and different database systems. To help you better understand data isolation between modules, let's look at a few practical examples. So this is the first level of data isolation between your modules, which also translates into no isolation between your modules. What I mean by this is you're going to have just one database. Let's assume it's a relational or SQL database like Postgres, and all of the tables for your modules are inside of the same schema, inside of the same database using the same database type. If we take this one step further, we get to level 2, which is isolating your modules using schemas. And this is where I think most modular monolith implementations should start. So in this example, let's say we have 3 modules: the orders module, the users module, and the finance module. And all of these modules have a respective schema inside of our SQL database. However, we are still using the same database, which means that one module could try to read some data from another module. And we are also using the same database type. So that's another constraint we have to work with. We have to make our data model fit the relational data model in this example. One way you could improve the modularity of your system and the isolation between your modules when you are using schemas is having different connection strings for each schema. You are only going to expose the connection string with the access to a specific schema to the respective module. The other module won't be allowed access at all, and if someone tries to query data from a schema that they cannot access, they will get a runtime exception. Taking the logical isolation in the database further, we can elevate it to physical isolation. So each of our schemas could be assigned to a standalone database. I'm not necessarily saying that all of these databases should be on a standalone database server. One database server can host multiple databases, and you can actually use this to your advantage. This approach also has better security because each of the databases will have a specific connection, and you will not be able to query the data from the databases that you do not have access to. If you think about this a little bit more, it's very similar to the concept of modular monoliths, with the logical isolation of the modules inside of a monolith application, and then elevating these logical boundaries or modules into physical boundaries inside of a microservices system. So this is just the same idea applied to databases. And the last level of data isolation between your modules is practically identical to the previous one, with the difference that we now allow having different database types. So we could have a document database for one of our modules, a graph database if relationships between the entities are very important for another module, and we can also continue using a relational or SQL database for another module. My recommendation is to always start with at least schema-based isolation for your modules. This type of data isolation is purely logical. All of your tables are still inside of the same database. You can decide to also allow foreign key constraints between tables in different modules so that you can have referential integrity, but I normally don't use this feature because I don't want to introduce that kind of coupling inside of my database, and I can just as easily control referential integrity from my application. When it comes to sharing data between modules, the general rule of thumb that I like to follow is to never integrate on the database level. In practice, this would mean that the modules are allowed to query data from some of the other modules, and this introduces very tight coupling between these modules, which is what we are trying to avoid when we are implementing a modular monolith. Of course, you can't build a complex system without your modules integrating in some way. So what do you do if you need the data from another module? You have a few options, and I'm going to list some of them here. The first option is you can just call the public API of the module that owns the data that you require and request to get the data back. This is simple to implement, but it increases your coupling to that module. Another way you can share data between modules is using messaging, and in particular, sending messages that contain all of the required information, which allows each module to store a local copy of the data that it requires. From my experience, this is a better way to integrate between your modules, so your modules will communicate by sending events, and each module can store a local copy of the data that it requires. This does introduce some eventual consistency into your modular monolith system, but most of the time this isn't a big problem. And there are many ways how you can deal with this, and I'm going to show you how when we start implementing our application. And the big benefit of storing a local copy of the data that you need is you do not need to call any other module to perform your business operation, which makes your modules independent and loosely coupled of other modules, which is pretty much what we are trying to achieve with this architecture. So let's do a recap of the module constraints that the modules in our system need to follow so that we can build a system that consists of isolated and independent modules. So we want to enforce logical isolation between our modules. Our modules must talk through a public API, which could be implemented in a synchronous way using method calls or asynchronously using messaging. And the last constraint is that our modules must be isolated in the database. If we manage to enforce these three constraints inside of our modular monolith system, we are going to end up implementing a very powerful and flexible application. And this brings us to the end of this lesson and also the first chapter, where we introduced the concept of a modular monolith. We started by comparing the monolith and microservices architectural styles. We talked about some architectural drivers that can help us decide what is the correct architectural choice to make in a given context. Then we introduced the concept of modular monoliths, and we finished off by talking about module constraints that we need to enforce in order to build a flexible and loosely coupled modular monolith system. In the next chapter, we are going to talk about defining your module boundaries using techniques like domain-driven design, bounded contexts, and event storming. I'm also going to introduce the system that we will be building inside of this course, and we are going to implement our very first module.